Now that we've talked about finding antiderivatives, we're going to introduce a little bit of new notation. And we'll explain it in much greater detail, and it'll become much clearer where this notation comes from in the next chapter. But for now, we're going to think of it like we have with the derivative operator. So our derivative operator, d dx, we have used now through most of the course. And this tells us when you're taking the derivative of a function, d dx, with respect to x, then we get f prime of x. We get its derivative. And so we're going to use notation that's similar to that called the indefinite integral of f of x. And that's going to tell us that if we're given a function whose little f of x, whose general antiderivative is capital F of x, then the indefinite integral defined with this symbol, and we do have to specify that we're finding that indefinite integral with respect to x, that's what the differential right here is representing, dx, is equal to that general antiderivative for all x in the domain of little f of x. So this is our new notation, and again, it will become very clear where this notation comes from in the next chapter. But for now, we can utilize this notation when we are working with finding antiderivatives. So finding an antiderivative, we will often say find the indefinite integral. That's another way to say find the antiderivative. So let's just look real quick at a quick example, like if I wanted to find, if I saw this, if I wanted to find the integral, indefinite integral, of sine of x with respect to x, dx, that is asking me, that notation right there is asking me to find the general antiderivative of, in this case, sine of x. So what is the general antiderivative of sine of x? See if you can think of that. So what function, when we think antiderivatives, and we do have to wrap our head around the fact that now we're going the opposite direction of what we have been doing throughout all of our chapters on derivatives, but we're saying what function has a derivative of sine of x? And it turns out that that would be minus cosine of x. Now, of course, we have that antiderivative, we have that, when we take the antiderivative, we will have that constant. We can think of it, you can always think of it as the fact that you would lose that constant going back the other direction. Okay? And we could continue with this notation. So we could say, I don't know, let's find the integral of 5x to the 7th. And I won't write it out again, but that's saying find the general antiderivative. So we're saying what function has a derivative of 5 times x to the 7th, and we'll use our power rule on this one. And so we would get 5, we have that constant, so we'd have 5, and then we'd get x to the, since we're finding the antiderivative, we'll increase the power by 1, x to the 8th, and divide by 8. And then again, we're going to have that constant. Okay? Sometimes we refer to that constant as the integration constant, because this process of finding the antiderivative is called finding the indefinite integral. So 5/8 x to, I was going to see if I could simplify. I don't know. I just ended up rewriting it. It didn't, definitely did not simplify. Okay. So that is just a new notation, and we're going to apply it to a couple of examples, more examples on this video. But before we do, let's just take a look at our table. We had a table of antiderivatives. What we could now do is we could just redescribe those as a table of integrals with this new notation. So let me pull that up on the screen. So here are those antiderivative formulas that we had talked about in the previous videos. Basically, every derivative formula that we now have an antiderivative formula for, or in our new language, we have an integration or an integral formula for. So you can see we actually just utilized, which one did we do? We did the sine of x. We just did this guy. We just used that integral formula, and we use the power rule too. So here's the power rule as well. So we have a whole set of integration or integral rules that we can use. And really, it's just our antiderivative formula is just being re-described, I guess, with this new notation. Okay, so keeping those in mind, and again, these are ones that while you can reference a table for these, you really want to know these ones. The ones that are on this table are ones that are going to be needed for the course. You want to have these memorized, put them on flashcards so that you can get them memorized. These are the formulas that we're going to definitely be working with. So let's start with this example. So if I come across a problem like this and it has that integration symbol, the integral of, and then in this case I have this rational function, and we're being asked to find that integral with respect to x. We're going to find the general antiderivative of this function here with respect to x. Now, this is a quotient, so in its current form, I don't have just a basic rule to apply to it, but I have algebra that I can use to simplify this first. So that's what I'm going to do to start off with on this problem. I'm going to simplify first so that then I can apply my general integration, general antiderivative formulas. So to simplify, since I have a monomial single term in the denominator, I'm going to go ahead and divide each of the terms in the numerator, and we'll do some simplification as we go here. So we would end up with just 2x on the first term minus 4 on the second term plus 5 over 2, there'd be just 1x in the denominator on that next term, minus 5 over x squared. And we are finding that integral with respect to x. So now what we have is we have a series of terms that we're adding or subtracting, and we can look at each one of these terms individually and think about which rule to apply. Now, we can apply the power rule or the constant rule on all three of the terms I have underlined here. 2x is just x to the first. This is a constant. This guy we're going to want to rewrite as 5x to the negative second power. But this term here, actually, I'm going to rewrite that as well. Maybe it'll become a little clearer. This is the one that we cannot apply just the basic power rule to because it's x to the negative first power, or 1 over x. So maybe if we write it that way, it becomes a little more clear. That formula, the integral or the antiderivative of 1 over x is the natural log of the absolute value of x plus c. Now that is in our integration formulas, but hopefully we've had enough experience now with taking derivatives that when you see a 1 over x, and sometimes for me I have to pull the constant off and then it becomes really obvious, that 1 over x, but hopefully we can recognize that, because if we were to try to apply our power rule and add 1 to that exponent of -1, we'd get 0, right? And division by 0, and we can't do that, right? Whole set of problems trying to apply the power rule to that because it's invalid. The power rule that I'm referencing here, if we have x to the integral of x to the n, that is equal to x to the n plus 1 divided by n plus 1 plus c when n does not equal -1. So that's right, kind of going in the back of our heads. Keep that in a little bubble because we do apply that a lot when finding antiderivatives or integrating. But it doesn't work when when the exponent is -1. That guy has an antiderivative or an integral of the natural log of the absolute value of x. Okay, so let's just finish this off now that we've had that little side conversation. Let's finish by taking the integral, finding, and for the first couple examples, I'll keep using that language. Let's find the integral, which means find the antiderivative of this function that we've now simplified and broken up so we can see how to do each piece. So we'll get 2 x squared over 2, because remember that was x to the first, minus 4x plus 5 halves times the natural log of the absolute value of x, minus 5x to the -1 over -1, plus a constant here. And that general antiderivative will always have that plus c on it, because if I were to check and take the derivative of c would be 0. All right. And my final answer for this integral, x squared minus 4x plus 5 halves, natural log of the absolute value of x plus 5 over x plus c. And there is my solution. I'll erase the highlighting from above. Okay, let's take a look at another example. So on this example, we want to find the integral of this function. This is a trig function, combination of two trig functions. And when we say, we remember again, we're using this new notation. So when we're using this integral notation, we're saying find the integral, which means find the antiderivative of this function with respect to x. Okay. So how are we going to do that? Well, let's pause for just a second on this, because notice here we've got a 4x, we have the sine of 4x, and we have the secant squared of 9x. So I want to pause for just a second and do a quick little recall on the chain rule. So a recall on the chain rule. If we were taking the derivative of a function that had a constant times x, so something like e to the 5x. Okay? When I take the derivative of that, I get the derivative of the function, e to the 5x, but by chain rule, I then have to multiply by 5. So when I take the derivative of f of kx, I would get the derivative, f prime, of kx, but then I would have to multiply by k. Now, we've used this rule a ton, all the time. It should be almost like second nature. We're just running through a chain rule. We've got a constant composed into a function. We'll multiply by that constant when we're taking the derivative. But what I want to do is I want to extrapolate now, and I want to take that and say, okay, well, but what if we're finding an antiderivative, right? So now let's expand on that for a second, and let's think about, well, what if I'm integrating a function that has a constant with respect to x? And I should have said here, k is just a constant, like 5. And so our example that we used up above, e to the 5x, let's do the same thing. If we were integrating e to the 5x, we were taking the integral, finding the antiderivative. Well, let's think about that for a second. We would get the general antiderivative, and what we're going to end up having is 1 over k plus a constant. Now, the reason for that is because we have to, right, we're going opposite. We have to undo whatever would happen going the other direction, right? If I were coming back this way and taking the derivative to check my work, since I have the constant, when I take the derivative, I'd multiply by k. So if I'm finding the antiderivative, then I have to have a division by k there to counteract that. So essentially we're thinking of, how would I undo that chain rule? So when I have e to the 5x, it might make more sense if we do this particular problem. If I find the integral of e to the 5x, again, exponentials, the antiderivative of e to the x is e to the x, so we would get e to the 5x, but we would have a 1/5, 1 over k, plus an integration constant. And so just a quick little note on that, right? If I were to check that, right, we can always check our integration work because we know how to take derivatives. So 1/5 e to the 5x plus a constant. If I take that derivative, you got that constant, 1/5 e to the 5x, you have to apply chain rule, times 5 plus 0. And notice having that 1/5 right there was necessary because of the chain rule. And so look, there's our work. This is a quick check. You can always do a quick check. All right, so that was a little bit of a sidebar on that, but I wanted to mention that because this is an important rule that will save us time if we can remember that. So anytime we have a constant composed into a function, when we're finding its antiderivative or integrating, we'll adjust for that constant with that 1 over k, that multiplication by 1 over k. And I'll show you how that would work on this particular problem. So I'm going to go ahead and bring that problem over here so I have a little more space. So if I was integrating 3 sine of 4x minus 2 secant squared of 9x dx, rather than applying what's called an integration technique, which we will start to learn more and more of those integration techniques in the next chapter, rather than applying that, if I just remember this little rule with the constants, I can think, oh, okay, well, if I want the antiderivative, I can think of what would be the antiderivative, or what is the antiderivative of the sine of a constant times x. Well, that's going to be, and remember the constant just stays out front. So we have 3 times, we will end up with minus 1/4 cosine of 4x, making that adjustment and thinking about antiderivatives or integrals. Minus 2 times, we'll have that 1/9. Now, the integral of the secant squared of a constant times x is going to be the tangent, because the derivative of the tangent is secant squared. So again, kind of remembering all of our rules here. And then, of course, we have the integration constant. And this would become minus 3/4 cosine of 4x minus 2/9 tangent of 9x plus c. Now, of course, we could come in here and we could do a quick check and take the derivative. And you will see when we do take the derivative, because of the need to apply the chain rule, when we take the derivative of minus 3/4 cosine of 4x, we would end up with a positive 3/4 sine of 4x times 4. And the 4 and the 1/4 would cancel, bringing us back to the 3 sine of 4x. Okay. So that's a very useful rule. Wanted to do an example on this video with the integration, just to mention that, because we are going to utilize that quite a bit when we get into integration and finding of antiderivatives. And while there are other ways to do it, and there is an integration technique that will allow us to do it, if we remember when it's just a constant that's being composed, a constant times x that's being composed, then this is a quick way to deal with that.